So far, we saw the basic concepts in predicate logic. We defined the first order logic, including three sets: the set of variables, the set of predicates, and the set of functions. Then we defined what an atom looks like. Then we defined what a term is. Now it's time to complete our mission to define what formulas look like, because we are about to construct formulas, you see, because we want to formalize statements. What you can see now on the screen is the definition of a formula in propositional logic. And what we are going to do now, we will alter this definition to predicate logic. So let's start with the first sentence. Given a finite non-empty set V of Boolean variables, of course, this must be thrown away. And instead of this, we should write something like that. Given a first order language, which, as you know, consists of three sets: the set of variables var, the set of predicates pr, and the set of functions fn. Okay. A formula is an expression defined as follows. The first option gives you the simplest possible formula. In propositional logic, this can be a Boolean variable. However, now in predicate logic, it can be a parameterized predicate, or in other words, an atom. So instead of a Boolean variable, we can use an atom. We already defined what an atom is, but let me just redefine it. So an atom is actually a predicate with actual parameters, in this case n parameters, where p is a predicate from the set pr, and the number of required parameters is n. And we also have to say that every ti is a term. This is something we already discussed before. This is the definition of an atom. Okay, what's next? Well, once we constructed atoms, we can start to use operators. We can use the same operators as in propositional logic. If I have a formula, I can negate it. So therefore, item 2 here is not needed to be altered. The same happens with item 3. So we can use conjunction, disjunction, implication, equivalence, and XOR in the same way as before. And finally, this additional constraint at the bottom: every formula is formed by applying those rules infinitely many times. This is not about to change, of course. But something is very much missing here. And these are one of the most important tools in predicate logic, the quantifiers. So there are no rules for quantifiers. So we need to add an item 4 here. And let me just write here what is the content of this item. So a formula can also be a quantified formula, right? It can be either a universally quantified formula or an existentially quantified formula. Both of those quantifiers must be followed by a variable, which must be followed by a formula, any formula. So basically, those two kinds of expressions are also formulas if the following constraints hold. First of all, x must be a variable. There is no other option. You must not use a constant right behind the quantifier or a function or a predicate. You must use a variable. So x must be a variable, and this is easy to formalize, because in the first order language there is a set that includes all my variables. So basically, x must be an element of var. And I must say something about a. Well, a is a formula, any kind of formula. So this concludes the definition of a formula. As you can see, it really resembles the formula definition in proposition logic, but we needed to alter it in several ways. I would like to highlight the usage of atoms instead of Boolean variables, and also the addition of quantifiers.